Okay. I know nobody's really up for listening to me talk for an hour anyway, so, you know, get to save on a few minutes of it today. I'm leaving the hat on. It's just not working. I'm having a bad hair day. So let's talk ComNets a little bit more, okay? A couple of things I want to do with you today. I want to extend out the conversation we were having about the elements that make up a convolutional neural network and their utility, as well as some of the ways in which they have similarity to basic fully connected networks, but also the ways that they do some things that are a little bit different, all right, especially with regard to things like sparsity, which is interesting because we can accomplish sparsity in a network. So we have an understanding that a network is traditionally considered fully connected. We're talking about something that is inherited from that restricted Boltzmann machine, right? The fully edge-connected network that has selections pruned to where only has feed-forward components. In the same way that a neural network at each relevant layer effectively operates on and transforms the inputs from that layer as if they were features, and each of the neurons technically responds to some pattern of information coming into it, all right? That pattern is a result of both the weights and the activation function working together, but it in fact can respond to specific characteristics of the network of inputs, okay? That would be the feature vector. In this particular case, we're going to deal with and leave the feature vector in its two-dimensional matrix form, and we're going to utilize the convolution operation to apply matrix form weight to it. So you can think about this operation as effectively an area network version of a neural network. Remember when we talked about receptive fields on like the surface of the skin, right? There's like an area that a series of nerves connect to in three-dimensional space. You can also think about the idea of the kernel size operating on the input matrix as a receptive field. And many times it is even called that, all right? So that kernel matrix operating on that visual space is a bit like, if you wanted to extend the analogy out, it's a bit like a series of neurons in your retina responding to the picture you're looking at. Now, what the difference is between that is technically the whole retina is responding to all visual space simultaneously. There is a trick to this and the effect that we can accomplish this functionality in kind of a really interesting way, and that involves an operation where we convert it into something else and then we perform another operation on it, all right? If you guys have all done convolution, you know what 1D convolution looks like. That's a function operating on another function. Effectively, it is related to shifts in range and mode of the output of that function operationally, once again, a transformation. In this particular case, we get a matrix that is reduced in size unless we do some special stuff to it, okay? One of the operations we can do, we said previously, that since there isn't adequate space around the outside of the image to accomplish getting a perfect one-to-one copy, right, the exact scale, that we lose some around the edges, we trim around the outside, we can actually pad the outside. We can either put zeros around the outside, or we can copy some of the data around the outside. We can make it we can make the mesh sort of spherical, such that whenever you run off one side, you effectively come back on the other. Have you guys ever played Asteroids, the game Asteroids?
Yes.
Right?
Yeah.
Go off the window this side, come back on this side again, right? That's how the convolution works whenever you're using edge padding in that case, all right? So you can technically pad an image to be able to get an image that's exactly the same scale as the original. There are upsides and downsides to that, partially because one of the things that we're actually looking to accomplish here is something that we've talked about a little bit initially, but we probably talked about pretty extensively within machine learning and AI in general, and that is when you have very, very large search spaces, when you have very, very large sets of possibilities, what's one of the first things you always want to accomplish? You want to whittle that down. You want to cut off all the things that don't make any logical sense for that to be. And as a result of that narrowing of possibilities, you reduce from a theoretically, unsolvable or untenable problem, right? Something that would take too long to search through all the possibilities for. And instead you narrow it down to a series of possibilities that are much more appropriate to the task at hand. Convolution does a dimensionality reduction operation that is simultaneously informationally preserving. In that sense, it is kind of akin to some of our information projection mechanisms, such as the principal component analysis style design, right? The idea being that the features that were present in a higher dimensional space can now be represented in a lower dimensional space, right? A 32 by 32 matrix going down to a 15 by 15 matrix, but not losing a lot of the representational power thereof, because the components that were most important to that receptive field have been maintained, okay? I mentioned that we do that, right? And I mentioned how we go about the process of the forward convolution calculation, right? We arrive at a convolved feature output for that array that is smaller than the original array matrix, okay? This is the process by which you might do it for a volumetric array system, right? And such that each of the two-dimensional matrices are treated as one layer of the tensor, right? And the filter is sequentially applied to the volume of the tensor. This one is something that if you guys really kind of want to watch through it, this animated AI GitHub is actually a really kind of neat space. They've got some other tensor visualizations for some advanced transformations that can sometimes be used in networks that we might touch on but probably won't spend a lot of time on because there's stuff there, okay? So right now we're just trying to build a network that takes in image data and outputs classification frameworks for the most part. We want whatever the largest volume content of that image to be recognized for what it is. If it's a picture of a lion, we want it to say it's a lion. If it's a picture of a car, we want it to say it's a car, etc., right? There is a more sophisticated functionality that we'll talk about later on in which the spatial elements of the image are actually recognized and they're quantified, spatially located, and projected back on the image, all right? That's a process we call segmentation. We talk about it at a very high level. Typically, in most of the classes you might be involved with image processing, the mechanism by which the convolutional neural network utilizes its responses to the CompNet in order to determine the actual localizations of the pixels in the space. That process is kind of a backprop optimization framework, but also at the same time, these systems are so deep, which you'll see in a little bit when I'm going to show you some of these nasty ones. They're so deep that we really don't backprop all the way through them in the traditional sense, okay? We're going to use some greedy, layer-wise, module-wise methodologies to locally optimize for performance. I want to talk to you about the idea of kernels and kernel optimization for a moment at this point in time. This information is available in the text. I feel like dropping it out into something that's sort of dry and boring probably isn't of high utility for you guys. My main goal is you can read a textbook, you can watch videos online. My main goal is to try to see if I can say it slightly different, if I can get a conceptual framework for you guys. Imagine that you have like one of those little decoder ring things that was on the back of like a cereal box, right? It's like a matrix that's got little holes cut out of it, like a mask operation. You're sliding it over top of a grid of numbers, right? And there's a certain holes in certain positions that show you what the numbers underneath in that matrix look like. Okay, you remember this? You've ever seen, everybody kind of did something like this as a kid or has a basic understanding of it, okay? It's kind of a cryptography idea. I could hide a message inside of a matrix, right, by only exposing certain characters and numbers. Now that matrix, that array that you have, that little decoder panel, right, is effectively a pattern recognition system. I'm recognizing, I'm putting it down, I'm aligning it, and I'm recognizing the embedded pattern inside of that matrix. When the pattern is recognized, similarly to a traditionally forward-connected neural network, the activation function will maximize, right? The amount that that particular kernel is outputting will say this feature is present in this location. So if you keep moving that decoder across the panel, every place that a feature of the type that that panel is designed for is detected, it will max the output of the function, okay? The idea behind this is there are theoretically, okay, I'm gonna be honest with you and say theoretically, because when you go to higher dimensional kernels, this gets a little more difficult to describe, but there are theoretically a finite number of shapes, right, in the universe. Shape group theory kind of implies there might be like 213 unique ordered patterns of things that are effectively tiled throughout most of the rest of the world. One of the things that's interesting about that is we have people who get based upon their assumed contribution to a type of localized error that we're going to use as a categorical type error. And we're going to attempt to try to do that process in 2D space rather than what we were talking about beforehand as a standard vector times kernel operation. Okay. Convolution operation, where we have a volume of size, width by height by depth, right? What is depth in many cases? That's the number of instances. All right, so that would be if you had a series of pictures in your data set would be D, right? Every image has a width and a height, and the number of images that you're going to use in your training process, which in this particular case, we're going to run into a problem. This is the first time that I ever really ran into this problem, because prior to this, when I was first working on neural networks, I had plenty of memory, right? So you can load all of your samples in, and you can let the network train on all of your samples. All your training samples, okay? Not all of your samples, okay? I wasn't crazy, okay? Well, I was at times, I probably did that. But as I learned that process, what I realized was, if you have all your data, you're doing what? You're giving as much information to the network as you can. Thus, it should in fact perform better in the effect that it is making its decisions based upon the widest variety of samples for that particular data space. There is a problem with that though, and that is that if the network has enough flexibility, it can start memorizing individual samples from there. There's a way to do it such that we only give it a certain number of samples at a time. I've talked about this beforehand, but I'm going to talk about it now, especially with convolutional neural networks, because there just is not enough memory to train with all of the image samples in the data sets that we use for these systems simultaneously. We're not going to upload multiple millions of images together into the working memory of the system and attempt to try to drive it through. What else are we not going to do? We're not going to try to access the images off the hard disk, all right, while we're doing the backpropagation system. It would slow down the update process for both the getting the images into the memory in order to do the process and, you know, sort of copying things back out in order to be able to have it off of a hard disk. It just makes it inconceivably slow. Plus, where are we doing most of this processing? Anybody know? Anybody know that what the trick was that they came up with in 2014 that made this possible? I think
in the server?
Before. GPUs.
Yeah.
Right? And I say that and everybody goes, oh yeah. Okay. GPU is effectively like a whole nother computer that you install in your computer.
Yeah.
All right. It's got its own memory, it's got its own buses, it's got its own architecture, it's even got its own cooling system, you know, and maybe some sophisticated cooling system technically. So in a sense, we are offloading many of those processes into the GPU. The GPU is also in possession of some really fast memory that has some unique characteristics that allow it to do things with this data set that we can't really do elsewhere. So we're going to train the system usually on batches. That is subsets of the whole volume D. Now what we're also doing there is we're masking off a certain number of samples that we're going to allow the network to see at one time. It must, every time we go through the epoch, update the weights relative to the trained samples it has in place. So when one group comes through and the system updates, right, and then that group passes by, it could theoretically memorize some of the data that was in that batch. Here's the cool trick though. When the next batch comes along, right? It has to update its weights based upon that batch. What's it going to force it to do? It's going to force it to try to balance between what it thinks it's memorized and how to update the weights for the new data set that it's coming through. Batch sizing is a bit like a K-folding operation, right, where we're chunking up the data. And technically, we're just going to cycle through all of the data. We're going to randomly resubsample versions of the data points. Those are individual frames D within the stack. And we're going to put them through K number of filters, right, to their spatial extent F relative to stride S, okay? That means what is the filter sizing and how many pixels are we moving at per time we're going to apply the convolution operation. Stride size of 1 moves it over just once, stride size 2 moves over 2, stride size 3, etc., right? What are the reasons why we might want to do larger stride sizes? We have a bigger kernel, okay? And we don't want to end up coming out with something that has way too much dimensionality, the end space, for calculation timing, right? We say it's likely that the feature we're looking for is going to be detected at some granularity based upon resonance in that kernel. And I'll talk about what I mean by resonance in a minute. But the idea here is that we convolve and operate using a volume space metric, right, in which we calculate an output relative to the filters times the filter depth times the total number of elements within the sample system, and we end up with a unit space of K weights and balances, right? And what do we have? We have a giant chunk of data that we're getting and a giant chunk of operations that we have to perform every single time we're doing this. Technically, this is a lie. Let me tell you why. Because nobody does it this way anymore. This is what you will find if you look up the information on many websites, okay? But they are hiding something from you, similarly to the fact of what I'm still hiding to you about backpropagation. I'm working. I swear, I promise you. It's never going to live up to the hype, but at this point in time, I feel like George R.R. Martin, like getting told to write the last book, right? It's like, finish it. It's like, come on, it's never going to be as good as you guys hope it will be for as long as it's taken. But anyway, the point is that this is actually a lie. All right, this is how you would do it if you were going to go through and chunk it up manually and run the filter operation. There's a trick here. The trick is kind of cool. I'm going to tell you about it, and I'm going to talk about it again. It will be something that maybe comes up on part of an evaluation. I don't think it'll be part of the midterm necessarily, but we're going to talk about it at least, and that is visual spaces are two-dimensional, right? And thus, their frequency characteristics in 2 dimensions can be categorized as what's called a spatial frequency diagram. Any of you guys know what the Fourier transform is? You do know it? You've heard of it? You know how crunchy it is, right? Lots of numbers, right? If I take an image and I perform a Fourier transform on it, what I get out of it is a spectral decomposition, that is frequency relative to space, of the image components and characteristics. If I take the Fourier transform of the kernel, I also get frequency characteristics of the kernel space. If I multiply those two Fourier transforms together, the multiplication operation in the frequency domain is the same as the convolution in the spatial domain. I transform both, multiply them together, and then once I get the output for the multiplication, I do the inverse Fourier transform, and it's the same as if I had gone through and multiplied by the kernel in every single space. It's a neat trick. And the way in which we actually managed to be able to get this to work fast enough that we can train anything that we have, because if you didn't use that trick, you wouldn't be able to take advantage of a lot of the architecture of the GPU that's designed to be able to do that parallel processing for those type of frequency transform operations. So by changing the basis of the question that was being asked into another form, they were able to massively accelerate the operation of the convolution. So while I do expect you to at least basically understand what's going on here, right, and relative to the volumes we're getting, these mathematics aren't necessarily like hard and fast rules, okay? So have an understanding of it, maybe not like a memorization level, but have an understanding of what we're meaning by width, height, and depth, right? And then characteristics of the output of the space, right? What is the width of the output? What is the height of the output? What's the depth of the output, right? The depth of the output is always going to be K because it is one output for each kernel. The next is height, right? Height relative to the case is height 1 minus what? F, that is the spacing on the kernel, its size, plus 2 times the offset there, right? The P, which is the padding symmetry that's been put in place, okay? So you subtract the kernel size plus padding, right? And see whether or not you lost or gained. Or you can't really gain here, but you can not lose, right? You see, did you come out even, right? If you pad it appropriately, your kernel can be nullified from being removed from the scale, okay? And then the width also is what? Oh, excuse me. The height is also relative and divided by the stride. That is how far you're moving it per kernel plus 1, all right? And then the width is what? The original width minus size of the kernel plus the padding characteristic over stride plus 1, all right? Both of those two things are effectively transformed in the same way. It's just a matter of what you put forward. So the output of the scaling of the output is a volume described as W by H by D. D is also W by H by K, right? You could say the output is WH by K, that every kernel outputs one element in the new layer. Okay. Pooling operation. We talked about this one and I had some questions on it. I want to make sure I clarify. Pooling is a very simple operation such that if I have a four operator element cell that is described by a 2 by 2 with a stride 2 characteristic, I am going to take the max of the matrix produced at each local region and I'm going to output that max into a 2 by 2 matrix in this case. So a 4 by 4 matrix is re-represented as a 2 by 2 matrix with a 2 by 2 pooling operation. This is the max pool operation that does what? In the red space, what's the max? 20. In the orange space, what's the max? 30. 112 in the blue and 37 in the green, right? It's super simple, all right? What does this mean? Imagine that these are each activations of the kernel, feature kernel, at each of the relative spaces, okay? Since the kernel has been applied here, 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 and here, right? Effectively, these might all be levels to which we're detecting the feature. We should really be looking at it from the perspective of saying that we've probably detected it to a certain degree several times within that space, right? As the kernel is getting closer to the center of the feature, it should more strongly activate, right? As you align the thing up with what you're looking at and it gets into that optimal position, it should light up better effectively. So if we only keep those elements which are most strongly activated, we're going to be keeping the elements which are most correlated with the feature characteristics of the original spatial representation, right? And doing what with it now? Reducing it massively into a representation space that contains some of the original data characteristics, right? And I say some because not every kernel will be able to keep all the information, right? Matter of fact, this is actually a lossy process if you want to think about it that way. I only keep the elements that I'm concerned with at each individual person, right? Each individual kernel is a detector. Each of those detectors only is concerned with finding one type of pattern, but things are composed of multiple different types of patterns, right? So that's a consideration we have to put into play, all right? So this is one of the things that we needed to do to be able to talk about it. The next characteristic here is to say that pooling actually operates and accomplishes a process which is called downsampling, right? So downsampling processes, there's a variety of them, but we use the pooling operator in order to accomplish the downsampling within convolutional neural networks, all right? Everybody has probably heard of it, at least to a certain degree, if any of you have done image processing. We do like bilinear filtering in order to do downscaling or localized averaging. This is actually a localized max spatial pooling, right? So it's gritty. I recognize that it's gritty because if you look at it in this case, you can see that it's somewhat smooth here, right? But it already starts to transfer to pretty Minecrafty by the time we get over there, right? But anything that gets chunky, I'm always going to call Minecraft, right? Because I look and say it's sort of the voxel representation of natural space, right? We're doing that to a certain degree here because we are voxelizing natural space, okay? pooling operators effectively operate on the original volume, right? They affect the kernel spacing version, they pool and downscale, and we end up with a volume that is K still relative to the input space because we still have K kernel operators, but now we have a smaller height and width relative to the localized pooling space. Sometimes this can actually be accomplished even with some normalization techniques by taking volumes of the space as well, and by operating one-dimensional kernels, all right? A 1D kernel is just a vector kernel, and you can convolve a vector kernel through the matrix in the opposite direction. All right, we'll talk about that a little bit later. It's an interesting operation that's sometimes used to regularize or normalize or pull features out of sets of data that have temporal characteristics at play as well, okay? So one of the last things, not necessarily last things as far as from last lecture, but I guess you'd say last thing from last lecture, that I wanted to sort of reiterate for you and give you a visualization for is this concept of levels of abstraction with regard to feature information. We say that, if you think about it, you guys know the term abstract art. Right? You got people like Picasso, right? He's famous for his abstraction in art, right? It's a picture of a woman. Are you sure? Like, is this the right painting? Like, I don't know, it just feels wrong. Okay, the reason why is because it's so abstract that it has taken the notions of spatial information and just reduced it down to its most primitive constructs, right? What are the primitives? We have like squares, circles, triangles, right? Yeah. That's it. Everything you can make out of squares, circles, or triangles, okay? So some form of polygon, right? But characteristically, you can actually break almost everything down into triangles if you do it just right. So even circles are effectively compositions of triangles because there is no such thing as an arc, right? There's just a series of lines that we connect together, right? Remember we had that conversation originally. That matters to a certain degree because what we're thinking about here is saying that if we have a series of edges in which the line is slightly changing slope around the outside, guess what? Each of those is a feature relative to the space. Each of the images that we get out of it in the kernel will detect a slightly different and slightly more localized understanding of the activation of that feature relative to that space. It's doing what we're doing in our brain at a higher level. It's not just the feature as already described by the system. It's actually figuring out what is important about the image, okay? This is where AI to me started to get really cool when I first started studying. I'm like, it's learning, right? It's actually kind of like, it's thinking. Like, I can understand what it's doing, okay? It's all gonna break down eventually because of the fact that the thing that it's doing is really weird. But these low-level feature operators, all right, these are the kernel inputs. And then we multiply the original image space by the kernel inputs, and we see feature components or characteristics of those features that are line segments, corners, elements of components of the system, right? So low-level features come together to become mid-level features, right? We'd often say something like edges become textures, right? A texture is what? A series of edges. It's bumpy because we run our fingers across it and we notice it has different heights, right? So that bumpy operator, we can visualize and we can see a variety of different textures here making up what? How often that line at that angle intersects with that image frame. How would we describe that from a signal standpoint? How often per unit? Frequency, right? Remember earlier I was saying we turned it into a frequency transform in order to do the multiplication? We're finding the spatial frequency of changes in intensity in the pixels at those points. In the same way that the eye's activation to changes in light intensity at those points finds edges in natural space for our visual navigation, right? The next higher level version of it is to recompose mid-level features into high-level feature systems, and that is where Lego blocks, right? These are the Lego blocks, okay? You put the Lego blocks together, they become shapes. You put those shapes together, they become objects. Ceiling fan, this one here, I like that one. It's easy to think about. There are 5 individual blades on that ceiling fan, right? A ceiling fan blade is something that's relatively easy for us to visually pick out. Also notice, just like a duck, What's a ceiling fan blade look like, right? There's a million of them. It can be anything. There can be 5 of them, there could be 4 of them, there could be 12 of them, right? What's the difference between an airplane propeller and a ceiling fan, right? Orientation. So it's just a perspective of where it's at. So that's an interesting component, right? How is it that we're able to sort of pick out which is ceiling fan, which is airplane blade, right? By context. So there's some additional information there that has to be supplied by a higher level understanding. That we tend to note that if it's in this orientation, that it's a plane blade, right? But what happens if you're laying down and looking up at it? You'd still notice what it is. You wouldn't mistake it for a ceiling fan because of what? What's around it. So the context is the distribution of the objects in the space, and you can think about that as a set of features that are passed on to the next layer. Okay? We found the components, we pass those off. Those components get put together by the next layer. Then they pass it off, then they pass it off, then they pass it off. It's a bucket chain. Okay? It's a processing bucket chain. At every step of the process, we're either doing a convolution, we're doing a pooling operation, or we're doing some kind of maximization operational function. All right? The pooling operation is also accomplished spatially as the components are what? Further condensed with one another. So these are visual representations at a lower dimensionality that maintain the kernel's frequency characteristics with respect to its likelihood that that feature is present at that region of space. I feel like that was a lot of information in that sense. But it is true, all right? So most of that's true, at least I think it is. So when I say this, the kernel gets updated effectively by how well it does at detecting features. If you are a kernel and you don't detect any features, you're not a good kernel. Everybody should be contributing to the system, right? Everybody should be recognizing something and holding up their hand and saying, hey, I saw this thing. But if we went through the whole process and you're kind of sitting back and vaguely raising your hand, kind of not committed to the process, I'm going to say, okay, adjust your perspective a little bit. Look at it differently. Change the output because we need you on board. Because if you're being calculated and you're present and you're not detecting any features, you're not contributing to the success of the network. Do I need to tell you by how much? Kind of, but at the same time, I only need to tell you, did you activate? All right? The ratio of how well you activated relative to your peers is effectively a grading on a curve, right? So say, hey, you kernels down there in the bottom, you guys did not make it to the norm of operational maximization, right? And you guys up at the very top are finding only features that are like very, very common and high frequency. So imagine if we wanted to apply this process to linguistic structures, which 1D kernel operations do operate on natural language processing, right? We use convolutional operations to find patterns of letters. What if one of those kernels was just designed to find the letter A, right? It's just high frequency letter, okay? You found all the A's. Did you do anything? Did you describe anything? Maybe not, okay, right? It might not be enough information. You might want it to start, you've overemphasized its necessity to try to maximize spiking operations. So what you might do is use a bigger kernel. The bigger kernel will effectively dilute out a little bit of that spatial activity and get it to try to find something a little bit more morphically specific to that task. There's an interesting characteristic here because sometimes you're going to have a kernel that adapts to find color contrast. Sometimes you're going to find a kernel that's going to adapt to alleviate shadows or shading within the image to try to enhance those components or color spaces within the image, right? Some of them are just going to find hard lines. Some of them are going to find soft gradients and enhance areas where the change is more smooth and retain those as groups or clusters of smooth transitions. So we're going to take this process and we're going to do what? We're going to output it to trainable classifiers, and then we're going to update this or attach this to that last operator that we talked about early on when we were talking about the output of classification-driven neural networks, and that is the softmax operator, right? So the softmax operator is going to be applied as a way of determining which class each of the images belong to. Now I say this is a overmassive overgeneralization. Why? Because images can contain a lot of different things, right? You can, if I take a picture of the whole classroom, there's a bunch of people in it, right? So the classifier might just say people because it detected a person, right? And it detected several persons, so it would say people in general. But if there happened to be, take a picture of a park with a few dogs in it, now it gets ambiguous. What is it that you want to identify? So we had to do a little bit of pre-processing before we started shoving this stuff in the networks, where we had to make sure that the images contained mostly segregated images of unique content, right? So if it's a picture of a car, it was mostly just car, right? Maybe some grass, maybe some tree in the background, but at the same time, most of the image, right? Structurally, most of the image was car. So let's think about that from a frequentist perspective. If there's a tree in the background, and my network has been trained to identify trees, but the tree is relatively small, I might get tree as one of the outputs for the softmax, but I would get it at a much lower number. That's where we can utilize that information about the fact that those features exist in that feature space to do the process I was talking about before that we'll dive into a little bit more as we go further through ComNets. And that's the idea of saying, well, if there's a tree here, tell me which pixels you decided to make that tree based upon, right? Which area did you activate the kernel function at to be able to detect limbs, leaves, trunk, etc. So if I can do that and I can break that up spatially, now I'm having a relatively explainable AI experience, okay? I say relatively explainable because I'm gonna look at something with you here in a minute that is kind of funny, and that is that convolutional neural networks look relatively sane to begin with, right? A filter is applied to the image. We see a series of edges operating in space. But within a matter of moments, all right, afterwards, we've already gotten to a point which I'm not really sure what's going on here in some of these segments. There's a reason why I say it starts off looking good. It starts off looking like it's kind of thinking the same way we would if we were to start kind of labeling, tagging pixels, and drawing lines around the outside of a vague shape. But as it starts to get over here into the lower dimensionality spaces, it starts looking less and less like a car, right? And even some of the activation operations, where we're seeing activation operations happening here, become a little bit less obvious, okay? Let's see if I can open this. Come on. This is a link to a website that's called CNN Explainer, right? And we can zoom in a little bit on this. It gets a little poorly behaved when I start zooming in on it too much. But we notice the operations for the original kernels look good. They find good, relatively solid edge operations here, right? Involving through the space. So we see the edges being detected, etc. See if I can scroll over. It doesn't let me scroll over, that's the problem. So when it zooms in too far, I can't see it. This one's a little bit problematic in the fact that you can zoom in on it and you can actually see what the output is if you click on it this way, right? So I can take the image and I can see the image at this scale. We note here, we can see the convolution, see the activation relative to the max activation for the spatial already be putting in, right? I read there what the comb is, and I'm already taking max of the output comb for the region I'm convolving through. Why is it doing both operations together? Effectively, the pooling operation is a bit like something that we tack on to the end of the activation alpha, right? In a sense, maybe it is kind of like the activation function within the neural network typically, because it's going to keep and decide which spatially is more significant, right? So it's already sorting and filtering for that process. We're going to use the same sort of activation functions relative to the kernel activation as we do in other neural network spaces. But I say typically the activation function that's used with CNNs is mostly the rectified linear unit, right? The ReLU, the one that's linear past 0 and then just 0 otherwise in the second case, piecewise function. The reason why is because that allows it to be able to potentially train further past the system, okay? So I'm going to leave this to you guys to look at, similarly to looking at the version that we had for the TensorFlow playground, right? You've got to do a little bit of playing with it on your own in order to get the max out. We've already looked at what these networks look like for the most part, structurally and spatially. But this is your average network, right? Some of the earliest systems looked a bit like this: standard input, multi-layer inputs, pooling layers, fully connected layers in sequence. Com, pool, com, pool. That's a very common sequence, all right? The convolution of the convolution is effectively finding the features in the first order elements, right? So we said that if at the first layer, the components contained within it are activation to edge components, we need to get up to at least the idea of textures before they have anything meaningful in them. So we're going to start edges, then textures. Then we're going to pool that, and then we're going to pass it off, right? It's technically going to be still textures, but at the next layer is going to do what? It's going to operate on those textures and pull out objects or elements of the objects, right? And then pool those, etc., right? So the idea of one conv after pooling, giving you an extraction of the features as the inputs of the next layer, is kind of a way of upscaling, spatially upscaling to pass it off to the next layer. The spatial upscaling allows the information to be retained, all right? This is the interesting part of it. That an H by W matrix, height by width image, right? Originally 32 by 32. And you imagine that we get a 27 by 27 image, but we get how many of them? And the one we saw beforehand, it was like 15, right? So think about the dimensionality of that matrix relative to the original matrix. It's actually a dimensionality upscaling. We're projecting the two-dimensional image into a higher dimensional space, but we're separating out the features into each of those relative dimensions. So the image is now being handled as a volume, right? The image is now a volume split apart into each of its relative components. Those components are handed off to the next element in the system and dealt with as an array, as a volumetric array. So the information is preserved spatially by projecting it in a higher dimensional space. It's a bit the way that CNNs can kind of be said to inherit some elements of the kernel trick operation from the SVM. And the effect to say that if we project it to a higher dimension, now the components of the image are structurally separable based upon frequency components. Those frequency components can then be reduced in scale, right, and integrated and spatially compressed so that they're easier to sort out. So whilst the end process, right, does technically look smaller on a height by width matrix assessment, because there are so many versions of it, right, that mostly that same information was originally present in the image still persists. It's just been extracted, all right? You've heard that term feature extraction. CNNs at their most primitive level can be thought of as an automated, self-directed feature extraction process, meaning that we don't have to tell it what elements are important. It can figure it out on its own. And that is super, super important for us when we start dealing with multiple high-density systems, right? Okay, so this process here, the idea of image, operation conv, operation another conv, we notice it gets more and more granular through the system. Look how many representations are present of the individual spatialized versions of the original image by the time we get to the last layer of the system. Hundreds of representations now from one original representation, each one taking into consideration its own unique view of what it thinks is most important about the original image. They're also relatively low dimensionality, so they look to the system like a series of activations from a connected neuron. So now all we have to do is hook them up to a fully connected layer, right? And then they can become features for that fully connected layer to work on. Notice also that the output of this about 5 by 5 matrix, this is the interesting part. 256 by 256 original input image, right? And we get down to like maybe a 15 by 15 image at the end of the process. When I think about what the impact of taking that out to a vectorization, right? Take a 15 by 15 matrix and vectorize it. Think about how far apart the components of it get, right? It's nowhere near as far apart as those components could be in that original 256 by 256. So this concept of extracting the features and then compressing them, right, pooling them together and getting them down into a smaller representation space, means that the process that we have to do ultimately, which is that we have to vectorize it eventually to be able to pass it off to our classification network, right, it means that it's less impactive. It means that it does not distort the spatial information, because the spatial information has already been accounted for by the activation characteristics of the kernels. The kernel is showing that as a spatio-frequency analysis, not necessarily temporal, but spatio-frequency analysis, okay? That spatial frequency analysis then goes into this vectorized pooling operation, and then we note what? That this network fully connected to this one will give an activation at a specific neuron. It's the highest activation. We can either do max or we do soft max operation at that localization. That'll provide us with something useful in the effect of saying that the image has now been classified according to the 38 possibilities we had available to it. This particular one is a leaf, right, with some disease on it, and it's being assigned tomato blight in its end case. All right, some of you guys have already seen this image, but it's the best one I can come up with, so I want to say that this is the best case that I have. All right, I like it, I feel comfortable with it, and so when I feel comfortable with it, say, hey, sometimes seeing it more than once is not going to hurt you. You're just going to feel like, okay, I'm familiar with it, I'm getting the idea. Let's talk about some of the major architectures. I'm going to go through these relatively fast. We'll probably expand some of them, but at the same time, we might not go into extreme detail. And part of the reason why I say this is when you get to the point of starting doing projects with some of these, you'll have to probably try a few of these architectures or play around with them or get used to the idea of importing a network and trying it, okay? It's not as bad as it used to be. A lot of this stuff is borderline drag and drop because a lot of these classic architectures are often included or very easily accessible via the APIs for these CNN development library systems, right? So I say the two main ones we're going to be working with, which can do everything from a single layer, single neuron network all the way up to multi-high dimensionality convnets. We've got two camps. You guys know what they are, right? Torch and TensorFlow, okay? TensorFlow is Google's, Torch is Facebook, okay? They're both contributed to by a variety of other people, and there are some emerging platforms out there that are starting to kind of, butt heads with these environments, but I would probably not recommend that you attempt those implementations just yet because Torch and TensorFlow are so easy. The commonly maximally adopted platform, the reason why it continues to gain mass, right, the rich get richer, is because of its representation. There are so many tutorials for it, there are so many people that can help you find solutions, and having a relatively codified solution in here is probably preferable. At that level, my preference, because of my experience to be able to help you guys with implementation stuff, is going to be TensorFlow, okay? I can do Torch, and when it's in Keras, it really doesn't matter, because Keras is a library that sits over top of Torch and TensorFlow, and allows us to construct whole modules. Okay? You can say convolution and tell it what the size of that convolution is, and it will go into the code and write the Lisp to develop all that output, which is a massive chunk of matrix calculus, right, that we don't want to ever touch. Okay? We just want to let it be in the background. So Keras is a godsend to all of us who are doing that work, trying to understand how the morphology works. All right? If you ever do need to dig in any deeper on the other side, that you can even see what Keras is doing whenever it is modularly coding the TensorFlow, and occasionally you will have to dig in there if you need to fix something. Right? Sometimes there will be a dimensionality mismatch. It's not as common as it used to be, but what we'll talk about, there's a lot of things here, all right? There's a lot of small elements at play. We haven't even really talked about optimization quite yet, or hyperparameterization. We're still talking about network morphology. So within the next 5 minutes, I'm going to go through these next few, okay? Inception, all right? This is the meme, right? We must go deeper, right? So that every single one of these chunks is an inception module, and each one represents an inception module characterization. Each one has roughly the same morphology, and it's effectively repeated throughout the process. So each one is a continuous what? Abstraction methodology. We take the low level feature characteristics and continue to compress them and operate them at a higher level feature space. And by this, you can get to a space that becomes operationally compact enough such that the probabilities being output from that space become non-negligible, right? They're not so tiny as to be, ignored. They are dog at something like 5 to 10%, right? Or maybe even something like 70%, depending on how well this network is trained, right? So the main classifier module is at the end of many different inception modules, and then some auxiliary classifier modules that pass information along the way. Interestingly enough, one of the reasons why I wanted to show this is you can tap into the network along the way and actually get the features to drop out from whatever it's doing at that layer. Usually we want to grab them after a pooling operation, but you can even pass those off to other classifier networks at elements and steps along the way. So networks like the inception, compress, and expand the network over and over again to be able to pass that information on. AlexNet. Yep, it's as chunky as it looks, okay? This is one of the originals, and it's usually pretty good for, low numbers of output classifiers. It has 1000D softmax, all right? So you can do 1000 classifications. There's 1000 classes of information that's put in place here. Part of this, the reason why is there's a fairly famous sort of model zoo space image network called ImageNet that had 1000 classes in the end of it. So a lot of times we're going to compare performance of these models, of these sequences of information based upon that. All right, so right now this looks like chunks of cubes, like baby plaything cubes, right? It doesn't really track with you what's going on in the space. One of the things that I will say is it will make more sense later on when you start doing something with it, to the degree to which you can see how that size of kernel tends to impact it, right? Say, do I make it bigger? Do I make it smaller? How fast is the learning rate in this case, right? Does it need another convolution before it has another pooling layer, right? Do we add something like dropout along the way to try to make it more sparse? Those elements can come into play as we're making this happen. So people made these decisions about things like these networks, right? One of the other of them is called VGG, and we'll probably talk about this one maybe in a little bit more depth, but there is a weird characterization with the end case here, right, where we have this compression framework, and then we have what? An upscaling operation, and then a prediction and labeling characteristic. That is that idea of segmentation, right? I'm actually taking the information that was output relative to the classification and reprojecting it onto, so I upscale the output and I reproject it onto the visual space information as an overlay, all right? So this is just one way of visually representing it. Now the interesting part about it, this portion of it is just for us. Just for us. Right? The network doesn't need it. It doesn't understand it. No, it doesn't. It goes, why? I've already got the information in there. I don't need to re-represent it in a higher dimensionality. Network says, if you want me to do something with it, no, I don't need to upscale it again. Why? Why would it? It's just to take something that's been represented as a volumetric approximation of localized spatial frequencies and then show us something that humans can actually get, okay? This is the network going, let me explain it to you for your dumb little monkey brains, okay? It's trying to give us some explanation of what it's doing on the inside. We incentivize it to try to explain to us as well as possible what it's doing on the inside of the network. All right, some of these topologies get really crazy nuts later on. Obviously, this one's pretty nasty, but this one's, in my opinion, even nastier. All right, okay. ResNet can be hundreds of elements deep. ResNet 50, ResNet 100, ResNet 150. All right, each one of these are effectively trained networks. Interestingly enough, some of these networks are trained on so many images of so many different types that they've found a set of features within their convolutional kernels that are relatively universal to being able to find useful features from image data. Thus, we can apply what has been learned by another network to a new use case. We said there's no free lunch. We can't make one network that perfectly solves every problem, but we might be able to start off with some of the things we have learned, right? We learn from somebody else's mistakes, and we transition that process. It's called transfer learning, right? And I'll talk about that again later on. Taking information from a previously trained network, and then only selectively updating some of the weights and characteristics of the system right? Such that we can decide where within the system we're going to allow it to sequentially update its process. And there's even some tools that are coming out now that do a better job of that based upon localization of gradient approximation, right? One of them is called LoRa. So there's some cool stuff in here. There's always emerging things, and if you think that the reason, if I'm going to be honest with you, right, the reason why my preparation for this class always kind of takes up a good chunk of my week is I'm trying to figure out how to make it as engaging as I can, while at the same time talking about stuff that's somewhat modern. This is kind of a little bit outdated, but BGG and some of those other things are a little bit more up to date. But we're going to keep talking about, or trying to talk about stuff that becomes more and more modern. At the same time, we're going to talk about how we can practically implement stuff that's already out there. Okay, so the next assignment you guys are going to have, and I'm going to give to you a little bit later on, is we're going to start implementing the TensorFlow versions of those operations, right? We're going to do the same thing, or roughly the same thing as you did with your original Python code, and we're going to try it in Keras, and notice that it's like 5 or 6 lines, right, for the whole thing. So Keras handles a lot of stuff for us. All right, I'll let you guys go. Thank you, and I will see you again next week.